All right, so in our next section, we're going to be looking at solids of revolution. Now, I just want you to see how this purple two-dimensional region is rotating. You might say it's rotating around the x-axis. Take a look at the solid that you create, kind of neat looking. How about this two-dimensional shape, that's sort of that normal curve? It's purple. What if you take that normal curve and you rotate it around like the x-axis? Again, look at the shape that you get. We're rotating it around. Now I want you to start thinking about the cross sections you would get if you would slice this. Let's say you'd slice down on it. What would a cross section look like? This example is like a wavy shape. That wavy shape is rotating around the x-axis, and now you should be able to see the cross sections clearly as those black circles. Look, every cross section is a circle. Okay, now this shape should be a solid. It looks like it's kind of like a skeleton, but pretend that it's solid as it rotates around. So you would get a solid circle, even if you rotate like that wavy shape. Now here's kind of like a feathery shape, and we're going to rotate it a little more slowly around the x-axis. We're only going to rotate it once, so take a careful look at this object. What would happen if you slice it? Would you still get a circle? If you slice it down, would you still get a circle? Well, you might be saying yes, you might be saying sort of. Yes, there's something different about this cross section if you slice it. Now we're going to take the same feather and we're going to rotate it around the y-axis. Just want you to see that we can do a y-axis rotation. Do we get the same shape? And what about the cross section? This time if you kind of like lop off the top of the object. So I hope you were able to see from those animations that a solid of revolution is just that. It's when a two-dimensional region, a two-dimensional space, is revolved or rotated around the x or y axis. And when you do that rotation, you actually create a solid object. Now, just like we did in the last section, solid objects have volume. And to find the volume, we're going to need to think about the cross section. Well, the good news is that the cross section will always end up being a circle when we do a solid of revolution. That means that the area formula will also always be a pi r squared. It will always be the area of a circle. Now we will continue to use the integral, that is to integrate all of those cross sections. And when you integrate them, you actually are adding up all of those little volumes, those little slices. And when you add up all those little slices, you get the total volume. So you'll find that the integration doesn't change. Honestly, the only thing that changes is that we're now focused only on circles. So if you look at the wording of this first problem, the first thing we're going to need to do is we're going to need to visualize the space. We're going to need to visualize the area that's being rotated. And then we're going to focus on circles. We're going to focus on the cross sections of this solid of revolution. Now, if we were doing this in class, as I've said many times, you would want to participate. You'd want to actually graph this problem. I really encourage you to graph y equals x minus 3 squared on your calculator. If you're not ready to do that, push pause, go get your calculator. You see, I'm going to graph this, but on your calculator, you end up seeing more than you need. You see, when you graph x minus 3 squared, you're going to get a parabola that moved over to the right 3 units. But again, you're going to get more than you need. Okay, because what we want to do here is we want to start to pay attention to the language of the problem, how the region we're looking for is bounded by both axes. That means the region that we're actually going to rotate, that region is going to be in here. Okay, because this is a region that's bounded by the x and y axis and our parabola. Okay, so we're going to want to get rid of some of the graph, and we're going to now focus on what would happen if this region rotates down over the x-axis? Can you, first of all, visualize that shape? What is it going to look like? The best I could do is to offer you this type of shape. Kind of looks like a suction cup, except it definitely would be solid. It would all be filled in, but it would kind of have that curve like a suction cup. Now, if you slice that suction cup, as we showed in the animations, you're always going to end up with a cross-section that's a circle. And so what we're going to do is use the area of a circle formula, pi r squared, and get ourselves ready to find the radius. Now, the radius is going to be measured from the axis of revolution. So it actually becomes quite simple to realize that any one of these vertical lines that I'm drawing is going to be the radius. So as we saw in the previous section, that distance, that vertical line, is a y value, and the y value is really the equation. So just as before, we can say that the radius is x minus 3 squared. Now, we got to be careful here because it's the radius that's equal to x minus 3 squared, but there's already a square that's built into this formula, so we do end up here with a square square. This doesn't happen all the time, but the algebra in this problem definitely says that we actually end up with now an x minus 3 to the 4th power times pi to be our area formula. Now, there's something I want you to notice about this problem. And that is that whenever you have an x-axis revolution, that is that the region was going to spin around the x-axis, you always will have a radius that is described by a vertical strip. And just like we did a couple sections ago, that will then create a dx integration. So what that means is when it's time to create your volume formula, that you're going to be using x values. That means that my limits of integration are x's. That means that my formula that I write down involves x. Of course, it already did. And that means that we will be doing a dx. So let's talk about these limits of integration. They have to be the x values of the problem. So our eyes want to be looking at these two blue numbers, x equals 0 and x equals 3. Now it's time just to evaluate the integral. You actually could do this problem by hand. In other words, you could add to the exponent and divide by the exponent, which would end up being 5. And you actually could plug in 0 and you could plug in 3. If you used f and I and t, that would be fine too. Either way, we're going to end up with our final answer here of 243 pi over 5, or the decimal equivalent that you would get from f and I and t. Now, I don't know if you saw this coming, but what we're now going to do is we're going to take this same region, but this time we're going to rotate it around the y-axis. And this will allow us to discover a number of things. One of the things that we're going to discover is whether the answer ends up being the same. We're also going to discover how to do a y-axis rotation. If I could just draw this problem correctly. Here we go. So it's the same region, but this time we're going to rotate it around the y-axis. Now, when you rotate around the y-axis, you're going to want to think of your radii as drawn from that axis of revolution. So that means that now your radii are going to be horizontal distances. The question, of course, becomes, how do I describe a horizontal distance? Well, the answer is it's still going to be the equation, but this time it's going to be the equation when it's solved for x. So we're going to have to solve this equation for x by doing a little bit of algebra. Taking the square root of both sides is definitely required. And now as soon as you do that, you get plus or minus. That's something we're going to need to talk about. But let's add 3 to both sides and come up with our final x equals equation being 3 plus or minus the square root of y equaling x. Now, that should be how to describe these these purple horizontal distances. I say should be, but we're going to want to make sense of the plus or minus. You see, the plus or minus actually describes both sides of the parabola. That is the left-hand side that's already drawn here. This is the left-hand side. And the right-hand side that we really didn't use. So here's the deal. The right-hand side would actually be the plus part of this equation. The left-hand side would actually be the minus part. And it turns out that that's what we have here. We only have the left-hand side of this parabola. So my radius, to clean this up a little bit, is more appropriately going to only be 3 minus the square root of y. Now, some other things change here, which can be mainly summed up by this rotation box. And that is that when we rotate around the y-axis, yes, we're going to have horizontal strips, but we're also going to do a dy integration. You say, well, what's the big deal about a dy integration? Well, a dy integration is going to involve the y values. So now your eyes want to be looking at the lowest and highest y value, as opposed to, as in the other problem, the x values. Now, this blue dot down here would still be y equals 0, but this blue dot up here, maybe you saw on your calculator, would be y equals 9. All right, so now I should have still thought about this area formula. Honestly, the area is always pi r squared. I could have and should have thought about that maybe a few moments ago, but I'm still able to fill in my radius here, my radius that we found by solving it for x. But let's be careful. Don't do some bad algebra. Don't try to bring this exponent in. You're not actually allowed to do that. Rather, this statement right here, this will be the statement that gets plugged into my integral. But remember, this integral is now a dy integral. That means that I'm going to be using y values for my limits of integration. Of course, we found them. And I'm going to be writing my equation in terms of y. Well, yeah, that's why we have a square root of y in this equation, because it's in terms of y. Of course, from here on out, it's time to just evaluate the integral. That means either do the antiderivative, which you actually can't do because we don't have a method to deal with an inside that's a square root and an outside that's a square. But you use f and I and t, and you would be able to come up with your answer. Now, it's interesting here. Do we end up with the same answer? Well, we do not. That's because the truth is this area is quite a bit smaller. You see these radii that I drew right here, these radii would not create as large of a circle as the radii that we had from the previous area. So we end up with a smaller area, but that's because the shape that we made is actually a smaller shape, again, because the radii of these circles would technically be smaller. Now, take a look at this problem. This is a great problem for you to try on your own. What we have is a region that's bounded by a line and, once again, both of the axes. I'd like you to actually try to do the problem as an x-axis revolution and a y-axis revolution. So we're actually trying to find two different volumes. This gives you a great opportunity to kind of practice on your own. Can you set one of these up? Can you draw the strips either vertically or horizontally? And can we end up with our final volume? I'll meet you back here in a moment with some of the details with this answer. All right, so we have our region, and we're going to first rotate this around the x-axis. Now remember, for an x-axis revolution, you're going to want to draw your radii from the x-axis. So we want to be thinking about that radius, that distance, as being a y value, real simply just being the equation. So when you set up your volume, it's always going to be pi r squared. I am kind of skipping and just setting the whole thing up right away, which I give you permission to do, as long as you understand that when I plug this in, negative 2x plus 4, then I'm actually plugging in the radius. And of course, we're going to use the x values of this region. So it would be from x equals 0 to x equals 2. And all you got to do is integrate. Make sure that the first time you do one of these integrations is not in your assignment or on a quiz. You want to practice f and I and t. This could be a problem that you could do by hand if you chose to. The decimal value using f and I and t comes out to be 33 cubic units. Now, for the dy integration, you're going to be rotating the region around the y-axis. Maybe you can kind of visualize the shape that you're going to get. But the most important thing here is to think about the cross-sections. And those cross-sections are still circles. and that means that we need a radius. This time the radius is going to be an x value, so you have to solve your equation for x. You can subtract 4, you can divide by -2, and we end up with this equation, -1/2 y, being our radius. Now, when you set up your volume, your integral, you're going to still integrate pi r squared, but this time, of course, my radius is described as -1/2 y plus 2. Don't forget the square. For some reason, that's something that's sometimes disappears from students' work, and I also will say don't forget the pi. For some reason, that can disappear. Because sometimes we focus so much on the hard parts, which is thinking of the y values and thinking about the cross sections, that we forget about the basic things. But I do need to use the y value since it's a dy integration, so that's from 0 to 4. And again, the rest of this is to evaluate the integral. Again, probably to use f and int unless you chose to work this one out by hand. By the way, the only way to work this out by hand would be to either do the FOIL method and expand the problem, or do a little mini substitution method with the inside. But we end up with 16.755 cubic units for that volume. Now, just notice that these two are not the same answer. In fact, it appears that it's exactly half of the answer. That's because the one cone that we made, did you realize that these are both cones, but the one cone that we made was a lot bigger than the other one. But it still gives you a chance to practice two different types of integration. Now, next we're going to take a look at a little different type of solid revolution, and I believe the best way to do that is through this example, where we have a region that's bounded by y equals x squared and y equals 4. Now we're going to try to rotate this around the x-axis, but mainly what I want you to be thinking about is what type of cross-section do you get? Let's graph it as we've done many times. I suggest that you graph this on your own calculator so that you can also start to visualize this. Actually, it may not even require a calculator because y equals x squared, of course, is just a regular parabola, and y equals 4 is just a horizontal line. Now, it is this entire region. That's because the problem says that it's the region bounded by these two curves, so we're going to use the whole thing. But what happens if we start to rotate this around the x-axis? If I was in class with you, I would try to help you see how the object is spinning off the board, coming back down to the bottom and back through to the top. So we spin this thing around the x-axis. What kind of object are we going to get, and what kind of cross-section do we get? So we take that curved region and we rotate it around the x-axis. Now, there's something different about this solid revolution. If you look very carefully, in fact, if you look on the inside, you'll see that it's hollow. Now, what does that do for the cross-section? Well, if you slice it, you find out that your cross-section isn't actually a circle, but it's a circle with a hole in the middle. Now, we will call this type of cross-section a washer. And you always wind up with a washer when you have a region that is hollow inside of your solid of revolution. Now, a washer is actually a metal piece of hardware that is circular but has a hole in the middle. So when we talk about a washer or the washer method, we're actually talking about one of these items. Now, what this really amounts to is, how do you find the area of a circle that has a hole in the middle? Well, the answer to that is really not that hard, because all you're really going to do is you're going to subtract a big circle, the area of a big circle, we'll call that pi big R squared, minus the area of a small circle, that is that circle in the middle. And when you factor out the pi, you end up with a nice little formula known as pi big R squared minus little r squared. And this formula is the one we will use for a cross-section that is a washer. Now, how do we know that we're going to need to use the washer method? How do we know that we're going to need to subtract out that inside circle? Well, if you go back to this problem that we were focusing on, the answer is actually quite simple. You see, when you have your axis of revolution and the region that you're rotating is not fully in contact, that is, you have this region in here that is hollow, then you're going to have an extra radius. We actually call it little r. Now, you'll still have your full radius. You'll still have your radius of your circle, and denoted here with this purple line, we can call that big R. But again, when the region is not fully touching the axis of revolution, then you're going to have a washer. Then you're going to need to use the formula pi big R squared minus little r squared. Now, it really just comes down to still trying to find these radii, and it's kind of interesting that the little r is actually the equation. Little r is given by x squared. But big R is a constant. Big R is always equal to 4. So when we go down to our formula, we're actually going to be plugging in a 4 for big R, but it does get squared, and we're going to be plugging in an x squared for little r. Now, that also gets squared, which gives us an example of a square square. Got to be careful with your formula, because what we really have here is pi 16 minus x to the 4th. So, volume, don't forget, is when you integrate all of these cross sections. And I want you to understand that this pi 16 minus x to the 4th, that's actually the area of a cross section. That's one of those washers that we cut out of the object. So when I integrate this, what I'm actually doing is stacking together all of those circles. Actually, they're washers, so that I can end up with the total volume. Now, it is a dx integration because all these lines I drew are, of course, vertical. So that means I need my x values of this shape, and x would have to equal 2, actually negative 2 and 2 for our boundaries. So we'll integrate from negative 2 to 2. Okay. F and I and T if you would like. Do it by hand if you would like. Sometimes students say, well, how would you do this by hand? You would have to change the exponents. You could add to the exponent of 16. That would give you 16x. You could add to the exponent of 4 and divide by 5, so it gives you 1/5 x to the 5th. But I would still need to plug in negative 2 and 2. And when you run that all through, you end up with 160 some square cubic units. Let's try another washer method problem. I want to make sure that you understand why and also how to use the washer method. If you look at this example, we have this blue region. It's, of course, confined by the square root of x, the x-axis, and also the line x equals 9. Now we want to take this region and we want to rotate it around the y-axis. We're going to rotate it around the y-axis. Kind of get a neat shape here. It is definitely solid and sort of has this open space in the middle. Now that open space in the middle is exactly what you want to be noticing, because the little r is always going to be the radius that is in that space, in that region that's not touching the axis of revolution. Your big R is still going to be the overall radius of your circle. So this is going to be a good example of the washer method, because the region is not fully touching the y-axis, which leaves us with that little r, shown here in red. And of course, we can define little r as the equation. Now, have you noticed that the equation needs to be solved for x, since this is going to be an x value? So we actually end up saying that little r is equal to y squared, the x equals version of this equation. Now, big R is going to be the equation, or the number 9. And we really have the two things that we need to be able to set up our integral. Now, keep in mind that this integral is going to be a dy integration because we are drawing the strips horizontally. So I am going to need to find the y values of this equation when it comes time to compute this. But it's always big R squared. It's always big R squared minus little r squared. And again, little r is y squared, but when squared is going to be y squared squared. In other words, 81 minus y to the fourth. Now let's talk about these y values. It's very tempting to look at this problem and say that maybe we're going to use or go from 0 to 9, but you see 9 is an x value. Your eyes want to be focusing more on the y values of your region, and especially this upper y value, which you could find by using a calculator or by thinking of the graph. That upper y value, 3, is really where I want to end. I want to go from 0 to 3, again, because this is a dy integration. We could pop this into f and I and t, find your volume, and of course we will have a shape that has a hole in the middle that is a washer for its cross section, and about 610 cubic units, which gives us a good time just to pause and see, when do I use the washer method and when do I not? Because I find that students start to want to make everything a washer problem. Now, it is going to be a washer problem if the region does not fully touch the axis of revolution. Again, you'll do the pi r squared, or excuse me, pi big R squared minus little r squared. But we've done plenty of problems where we didn't use the washer method, and that's because the region did fully touch the axis of revolution. There was no hole in the graph, so we don't need a little r. Now, when there's no washer method, you're just going to go back to regular pi r squared. Which brings us to this interesting problem where we have a region enclosed by the y-axis and both the cosine and sine waves. Now, we're going to rotate this around both axes, so it's going to end up being two different problems. But the first thing we want to do is we just want to identify the region, because I find that a lot of this becomes now a visual discussion on if students can decide where the region is so that they know if it's going to be a washer problem or not. Okay, good problem to put on your calculator. I'm going to also help you to see it. Of course, the cosine graph from your trig class starts up here and then goes on its way. A sine graph, it passes through the origin and then goes on its way. Okay, now I've seen the problem before, but would you be able to first of all identify that the region that we're talking about is in here? This is the region that's between the sine and cosine graph and is also butted up with the y-axis. You see, sometimes I'll have students find this region down here in blue, but that's because your eyes are focusing on the x-axis as a boundary. Again, this problem, we're using the y-axis. So we have our x-axis rotation. So now what we got to do is we got to decide if it's going to be a washer method problem or not. You should quickly be able to determine that the region is not fully touching the x-axis, which would give us, again, the two radii, that is the little r, and it would also give us the big R. So our mind should be spinning here trying to think, well, what would be the description for each one of these radii? It turns out that both of them are the equations. We just want to, of course, get them correct. The bottom equation is actually the sine wave. The upper equation is the cosine wave. But again, the main thing here is to understand that this is a washer problem when I rotate it around the x-axis, because the region is not fully touching the axis of revolution. So what that means is that I'm going to be using the big R squared concept, so that would be cosine squared, minus the little r squared concept, so it would be minus the sine of x squared. And we're using x values. Since this is a dx integration, we'll have to be thinking about the far left x value, which is actually x equals 0, and then this far right x value. Now, to find that x value, you might have to use your calculators intersect command, or maybe you know that sine and cosine intersect at pi over 4. But it would be a number that we'd have to calculate so we can fill it in here as our limits of integration. So the x-axis is a Washer method problem, and just so we have a number that we can look at here, we end up with 1.571, which happens to be the same as pi over 2. I don't expect that you necessarily would get that, but we can see our volume. Now, for our y-axis rotation, let's slow down a little bit because look, the region is fully touching the axis of revolution. So that means that this one is not going to be a Washer method problem. What that means is that I just need to start thinking about the radii. Now, this radii right here or this radii right here are fine, but there's something different about these two radii in comparison, and that is that each one of those radii are described by a different equation. You see, the red radii are described by the sine wave. Even so, solve for x, so we end up with the inverse of sine. Well, these radii up at the top are described by the cosine wave. And again, solve for x, that would actually be the inverse cosine. So it's not a Washer method problem. It's not using a big R and a little r, but it is using two different radii. So what happens here is that we actually have to do two problems. We have to do a pi r squared for our lower circle. So we'll call that the inverse sine of y circle. And then we're going to have to add to it a pi r squared of our upper circle. And again, that was with the inverse cosine of y. So we're actually subdividing the problem so that we can find each of these two circles. And we're going to have to subdivide with these three y values. Now, the lower y value was 0, and the upper y value is 1. But it's this middle y value that can be a little hard to find, and that would be the y value where these two lines intersect. It is the number root 2 over 2. Again, it's something that you might find with your calculator. It's intersect command. But I'll be able to use now these subdivided y values so when we set up our limits of integration for each of my two circles. Good problem to use f and I and t. You end up with two separate volumes, 0.4, 0.2, and when you add them all together, you end up with your total volume of this region. So not a Washer method problem because the region was fully touching, but it did require subdividing because we actually have two different radii denoted by the inverse sine and the inverse cosine graphs. Now, there's one last type of solid revolution problem to look at, and that is when you actually rotate around another axis. In other words, not the x or y axis, but another axis of revolution. If you take a look at this problem, we have a region. It's between the parabola and the x-axis. It would actually be this region in here because that's the only region, again, between the parabola and the x-axis. And it's now being rotated around y equals 4. It's being rotated around another line. Now, this would be an interesting object because if I would spin it, it would kind of like spin up and then come back through, and it would be spinning around and around. And can you picture the kind of shape that it would make? Well, it actually would look kind of similar to that Play-Doh shape I showed you a few problems ago. And the most important thing here is to realize that it is going to end up having a big R and a little r. The region is not fully touching the axis of revolution, so we're going to end up with a little r denoted by this radius, and then a big R denoted by this radius. So let's use the Washer method to find these two radii. Now, big R is pretty easy to see. It's simply the full distance up till that line, which will always consistently be 4. Little r, well, it's not just as easy as saying that it's equal to the parabola. Little r is not just equal to the parabola, but it does have something to do with the parabola. Now, what you want to understand here is that the parabola is actually this distance that I'm going to put in blue. you see that distance right there would be equal to the negative x squared plus 6x minus 5. So if we want to find the little r, we're going to have to do a little subtraction. It's the old adage where you subtract the full distance, that is 4, minus the little distance, that is the parabola. And when you do that subtraction, you will end up with the distance in the middle. So what do we get? Well, if you distribute the negative sign, you end up with a positive x squared, a negative 6x, but now a plus 9. And what I want you to understand is that that expression would be little r. Now, it's still a dx integration because we're doing this problem around a horizontal line. And further, the values in this problem are going to be x values. Since the equations that we have here, in other words, the big R being 4 when we put that in the washer method, and then the little r being the x squared, these equations are in terms of x. They're solved for y, but they're in terms of x. Now, this square that I put here, this is probably the most forgotten square because you already see a square from your equation. But you want to make sure that you're using the big R squared minus little r squared formula very carefully every time you set up a washer method. And so if it was me, I'd probably do a little simplifying here, maybe get like the number 16. But I would probably choose to just leave that other square when I go put this in a calculator. And again, I encourage you, put this in a calculator from 1 to 5 and make sure that you can actually get this answer. You don't want the first time you put one of these in your calculator to be on the quiz or on the test. So you do get 160. Double check that you have all the parentheses. Sometimes students miss a parenthesis and they wonder why their answer isn't the same. Sometimes it's this last parenthesis out here. But use all the parentheses when you plug in F and I and T. Make sure you can get 160 cubic units for this volume. Now, when you do your assignment, there's something I'm going to ask, and that is that you always make a sketch. Even if the book already has a sketch, I want you to still redraw the sketch so that you can show the radius or the radii, depending on if it's going to be no washer method or washer. And that way you can then set up your volume statement using pi r squared or pi big R squared minus little r squared.